Welcome to this physics video. In this video today we'll be looking at magnetic force equations. Now this is a second of a two-part series to do with magnetic fields and magnetic forces. So I would encourage people before they watch this particular video to have a look at the magnetic fields of video 1. It has this visual and it has a link here as well. Now this link I will place in the comments at the bottom of this video. So assuming you've watched that, let's make a move on to our second video on magnetic force. So back in our magnetic field video, we looked at a range of different hand rules, right hand rules, one of which was the right hand slap rule, and that was used to predict the direction of the force upon a current carrying wire that is located or positioned perpendicular to a magnetic field. So for recollection from our previous video, this is what happens. There's a force exerted upon the wire. The right hand rules serve a purpose to predict the direction of force. However, there's no quantitative calculations for the actual magnitude of the force. So the first of the three rules we want to look at today is a rule that allows us to calculate the newtons of force upon a current carrying wire that's positioned perpendicular to a magnetic field. And here's our equation, F equals NBIL, where F is the magnitude of the force, magnetic force, in newtons. N is the number of wires. There are some scenarios where there's just a single wire and other scenarios where there's a bundle of wires. B is the magnetic field strength measured in Tesla. I is the current in the wire that's perpendicular to the magnetic field, measured in amps. And L is the length of the wire within the magnetic field strength B. And it's measured, as always, in SI units in meters. So F equals NBIL. Let's look at our first example. A straight wire of length 25 centimeters carrying a current of 40 milliamps is placed in a magnetic field of strength 0.5 Tesla. Calculate the magnitude of the force exerted upon the wire. So let's extract our data. First of all, F, the magnetic force, is our question mark. L, the length of the wire within the magnetic field, is 0.25 of a meter. I, the current, is 40 milliamps. B, the magnetic field strength, is 0.5 of a Tesla. And because we've got a single straight wire, N equals 1, there's only one length of wire. Our equation is F equals NBIL. We substitute our values in. N, the number of wires, is 1. B, magnetic field strength, is 0.5. I, the current, is 40 milli, which is 10 to the negative 3 amps, and L was 0.25. And that comes out to 0.005 of a newton, which in scientific notation is 5 by 10 to the negative 3 newtons, which is commonly referred to as 5 millinewtons. Example 2, a bundle of 4 wires, each of length 40 centimeters, and each carrying a current of 800 milliamps, is placed in a magnetic field of strength 400 millitesla. Calculate the magnitude of the force exerted upon the bundle of wires. So extracting our data, we want to find F, the magnitude of the magnetic force, L, the length of 0.4 of a meter. Note, we can't leave it in centimeters. It must be in the correct units for this equation to work. So 40 centimeters is 0.4 of a meter. I, the current, is 800 milliamps. B, the magnetic field strength, is 400 millitesla. And N, the number of wires in this case, is 4. So we use F equals NBIL. And we substitute our values. N was 4 because it was 4 wires. B, the magnetic field strength, was 400 millitesla, and milli goes in as 10 to the negative 3 because this equation expects our magnetic field strength to be in Tesla. Likewise, the current is 800 milliamps, so we put that in as 800 by 10 to the negative 3 because this equation is expecting our current in amps, and we have here the length of 40 centimeters, which is expressed as 0.4 of a meter. That gives me a force of 0.512 newtons, or in scientific notation, 5.12 by 10 to negative 1 newtons. Our second situation, now we want to look at an equation that allows us to work out the force upon a charged particle in the presence of a magnetic field. So you recall the right-hand rule for charged particles. Effectively, it allowed you to predict the direction of the force upon a charged particle as it moved perpendicular to the magnetic field. So let's look at the equation we can use to calculate the force upon this moving charged particle in the presence of a magnetic field. So the magnitude of the force applied on the charged particle moving perpendicular to a magnetic field of strength B can be determined by the following equation. It is F equals BQV, where F is the magnitude of the magnetic force, B is the magnetic field strength in Tesla, Q is the magnitude of the charge in coulombs, and V is the speed of the particle in meters per second. Let's have a look at our third example. An electron is moving perpendicular through a magnetic field of strength 0.8 Tesla at 50 meters per second as shown in the diagram below. Calculate the magnitude of the magnetic force experienced by the electron, and we have there the charge of an electron is 1.6 by 10 to the negative 19 coulombs. Now note, the charge of an electron is actually negative, but in this calculation we're after the magnitude of the force, so we're going to use it just as a overall positive value. So F, the magnetic force, is our question mark. B, the magnetic field strength is 0.8 of a Tesla. Q, the charge of the electron is 1.6 by 10 to the negative 19 coulombs, and that would be given to you in a data sheet for a VCEE exam. And V is the speed of 50 meters per second. Our equation again was F equals BQV, and we sub our values in, where B was 0.8 of a Tesla, Q was 1.6 by 10 to the negative 19 coulombs, and V, the speed, was 50 meters per second. Multiply those three variables together, and we end up with a force, a centripetal force pushing towards the center of a circle of 6.4 by 10 to the negative 18 newtons. Example number 4. A proton is moving perpendicular through a magnetic field of strength 1.4 Tesla at a speed of 100 meters per second as shown in the diagram below. Calculate the magnitude of the magnetic force experienced by the proton, and we're given here the charge of a proton. It's the same to that of an electron in magnitude. So first of all, we're after the magnetic force, that's our question mark. Magnetic field strength is 1.4 Tesla. The charge of the proton is 1.6 by 10 to the negative 19 coulombs. And of course, V, the speed, is 100 meters per second. So we use the equation F equals BQV, substitute in our values, and we end up with a force of 2.24 by 10 to the negative 14 newtons. Our final equation is to do with the radius of curvature of a charged particle as it moves perpendicular into a magnetic field. You can see this quarter rotation of a circle is actually a part of a larger circular rotation. So this involves centripetal force. Let's have a look at the equations involved. First of all, we know the force on the charged particle, which was BQV, is now equal to the centripetal force, which will be mv squared on r. So there's our new expression. We can, of course, now manipulate that. So if we were to multiply the radius across the left-hand side and divide the BQV across the right-hand side, we have a new expression now to calculate the radius of curvature of a charged particle that has velocity traveling perpendicular to a magnetic field, and it is mv squared over BQV. Now, those who are tuned in will see that we've got a v squared and a v. We can further simplify that, dividing the v through on the bottom and the squared, which leaves me with r equals mv over bq. And mv, by the way, is momentum. It's another variation of this equation, where r is the radius of circular motion in meters, m is the mass of the particle in kilograms, v is the speed of the particle in meters per second, q is the magnitude of the charge in coulomb, and finally b is the magnetic field strength in Tesla. Example 5. An electron enters a uniform magnetic field with strength of 5.0 by 10 to the negative 3 Tesla, moving in a direction perpendicular to the magnetic field and turns through 1/4 of a circle. The initial speed of the electron is 4 by 10 to the 6 meters per second, as shown in the diagram below. Calculate the radius of the electron's circular motion. So we have here also the additional information, the charge of an electron, 1.6 by 10 to the negative 19 coulombs, and the mass of an electron, which is 9.1 by 10 to the negative 31 kilograms. Let's write down our variables. First of all, the radius of the electron's circular motion is the unknown. That equals question mark. The magnetic field strength is 5 millitesla. The charge of the electron is 1.6 by 10 to the negative 19 coulomb. The mass of the electron is 9.1 by 10 to the negative 31 kilograms. And the speed of the electron is 4 by 10 to the 6 meters per second. Our equation is r equals mv over bq. We sub all our values in, looks quite complex, do our calculations carefully, and we end up with a radius of 0.00455 meters, which could be written in scientific notation as 4.55 by 10 to the negative 3 meters, or more simply, 4.55 millimeters. Our sixth and final example. A proton is moving perpendicular through a magnetic field at 5.0 by 10 to the 7 meters per second, as shown in the diagram below. Calculate the strength of the magnetic field given it undergoes circular motion with a radius of 0.25 of a meter. And we're given, of course, the charge of a proton, 1.6 by 10 to the negative 19 coulombs, and the mass of a proton, 1.7 by 10 to the negative 27 kilograms. The magnetic field strength, B, is our question mark. The radius of curvature is 0.25 of a meter. The charge is 1.6 by 10 to the negative 19 coulombs. The mass of the proton is 1.7 by 10 to the negative 27 kilograms. And the velocity, or the speed rather, is 5.0 by 10 to the 7 meters per second. Our equation is R equals mv over bq. In this scenario, we have the switch. We are dividing the R across the denominator and we're multiplying the bq out to the left-hand side of the equals. So we now have a new expression, B, the magnetic field strength, equals mv over rq. We sub our numbers in, and we find the magnetic field strength for this example to be 2.125 Tesla. I hope this video has shown you how we can make quantitative calculations regarding the force experienced by a current carrying wire in the presence of a magnetic field, and the force experienced on a charged particle traveling perpendicular to a magnetic field, as well as the radius of the arc as a charged particle moves through a magnetic field and experiences circular motion. As always, if you've enjoyed this video, please like, share, comment, and subscribe. And once again, thanks for watching.